Today's lesson is going to focus on covalent molecules only and a new concept called polarity. When we talk about polarity of covalent molecules, there are two different kinds of polarity. The first type is bond polarity. And this is us looking at the electrons in a covalent molecule that are shared and trying to determine, are these electrons shared equally or unequally? Okay, so we know that the electrons are shared. Are they shared equally or unequally? This is a newer idea that you have not thought about in previous courses. So this is where our electronegativity values come into play. Remember that that term means attraction for electrons in a bond. Depending on the numerical value, one of your atoms may be more attracted to the electrons than the other atom, and then the electrons get pulled to one side versus the other within the bond. So you have to take the difference in electronegativity values. If the difference runs from 0 to 0.5, what that means is that the values, the electronegativity values of your atoms are very similar, very close together. And that means that they have sort of an equal attraction for electrons in the bond. And if it's an equal attraction, those electrons really won't be pulled from, one atom to the other. And we call this a non-polar bond. Okay, non-polar means equal sharing of electrons. If you do your math and you get a difference in electronegativity that falls in the range of 0.5 to 1.7, this is telling us that the electronegativity values for your atoms are not similar. One atom has a much higher value than the other and will have more of an attraction for electrons in the bond. This will result in unequal sharing, and we call this a polar bond. Okay, so you either have polar bond, which means unequal sharing, or non-polar bond, which means equal sharing. If you determine you have a polar bond, you have to do a little extra work. You have to actually show us within the molecule which way the electrons are being pulled. So if we look over here at these two images, hydrogen's electronegativity value is 2.20. Fluorine's electronegativity value is 3.98. This is quite a difference in our electronegativity. And if you do that math, you're actually getting a value of approximately 1.78. This actually goes above our range, but that's okay. Sometimes there's exceptions. And so what we do is we say, okay, this is a polar bond, and we draw this little dipole. We draw a little arrow, and we indicate that fluorine's going to grab the electrons for itself because he has a higher value. And if those electrons are being moved, okay, you don't need to write that in, but I'm just showing you, the electrons are being moved over to fluorine, hydrogen ends up with a more positive charge associated with it. So you have to draw this in now into your bonds. Here's hydrogen and chlorine. When we do their difference in electronegativity, we get 0.96, okay? This is also a polar bond. And this means that I now have to draw an arrow indicating that electrons are going to be pulled towards chlorine, which makes him slightly negative, and electrons are pulled away from hydrogen, which makes him slightly positive. And this is where these symbols, okay, they look like a lazy music note, I always say. That's the Greek letter delta. And we use that symbol to indicate partial charge, okay? It's not like ions, but it's just that the electrons are kind of being pulled in one direction, which makes the one atom more negative and the other atom more positive. I now want you to calculate the difference in electronegativity for these four sets of elements. And I want you to then label, does that difference in electronegativity indicate that these atoms will bond in a non-polar bond or with a polar bond? If it's polar, I want you to draw a little bond dipole like we just saw on the previous slide. So stop the video, carry that out, and then when you're done, come back and check your answers. Okay, so you should have done the math for these 4 sets and come up with the proper type of bond. So again, you have to know the ranges. And if we look at number 1, so chlorine and hydrogen, the difference in electronegativity is 0.96. This falls in the range of a polar bond. And if it's polar, we have to indicate who would be more attractive for those electrons. So we would draw a dipole over towards chlorine because he has the higher value. And we indicate that chlorine would be a little bit more negative and hydrogen would be a little bit more positive because chlorine's more attractive for those electrons. Between oxygen and fluorine, this is a value of 0.54, so it just squeaks in the range of a polar bond, but still means that fluorine will win. He's got the higher value. He'll be slightly negative, and hydrogen will be slightly positive because those electrons are more attracted to fluorine. Carbon and hydrogen have a difference of electronegativity of 0.35, which is a nonpolar bond. So when there's a nonpolar bond, you do not draw a dipole. No bond dipole. You leave it alone. Those are equally shared, those electrons. Do not draw a bond dipole. And then if you look at sulfur and chlorine, their difference in En is 0.58. Again, not very polar, but falls in the range. Chlorine's more electronegative, so you draw your bond dipole indicating the electrons will be pulled towards chlorine. So he becomes more negative and sulfur will become more positive. Once you establish the bond polarity, you now look at the overall molecular polarity. So this is the entire molecule, not just the individual bonds. So the molecules can also be classified as polar or nonpolar. And this is looking at the entire molecule and what's happening to the electrons within. So a nonpolar molecule is one which has an equal distribution of electrons within the molecule. So you're going to look at all the electrons and say, okay, how are they distributed within the molecule? If they're equally distributed, they're a nonpolar molecule. If you have a polar molecule, this is one which has an unequal distribution of electrons within the molecule. And similar to a polar bond, okay, so polar bond, you have to draw a bond dipole. Now, if you have a polar molecule, you have to show an overall dipole through the molecule, indicating where the majority of electrons are being pulled. So we're now going to apply molecular polarity to our covalent molecules. And there are 3 steps in order to do this. First, you have to redraw or draw your covalent molecules. This is step number 1, and this is what you learned in grade 10. Then secondly, you have to indicate the bond polarity. And then lastly, the molecular polarity. So there are 3 steps to this. These are the molecules we saw in our previous note. And I've gone ahead and I've drawn the covalent molecule or the Lewis structure for you already. So that would be step 1, is to draw the molecule. Step 2 is now for us to calculate the bond polarity. So we have to take the difference in electronegativity between, in this case, carbon and chlorine. So chlorine's value is higher at 3.16, and we're going to subtract off carbon's value of 2.55, and we get a difference of 0.61. That value falls in the range of a polar bond. And we know what we have to do. If we have a polar bond, we're supposed to go over to our bonds and draw which way the electrons are being pulled. Chlorine is more electronegative. This is chlorine. So what we're going to do is we're going to draw bond dipoles indicating that electrons are being pulled towards chlorine in this molecule. And in all of these cases, carbon becomes more positive because those electrons are being taken away from him. Then what we do is we look at this molecular polarity, and we look at this overall molecule and we say, is that an equal or an unequal movement of electrons? And this is an equal movement. If you look at this, and I'm just going to use a different color here to highlight, I have a movement of electrons going up, and I also have a movement of electrons going down, and that movement cancels itself out, and we say that that's an equal pole. If we have a movement going to the right, we also have an equal and opposite movement going to the left. And so that would cancel itself out as well. So overall in this structure, we have an equal distribution of electrons. This is a non-polar molecule. Let's look at the next example, which was oxygen. So we did our Lewis structure for oxygen. That would be step 1. Step 2 would be to calculate the bond polarity. This one's easy. Difference in electronegativity. Oxygen is the same, so we're going to subtract 3.44 from 3.44, which is 0. And we know that that would be a non-polar bond. So you have to write that in. And if that's a non-polar bond, remember, we're not drawing any dipoles. So those electrons are perfectly shared within the molecule. And then overall, they're not being pulled in one direction or the other. So it's an equal distribution of electrons. This is also going to be a non-polar molecule. Let's look at our last example here of phosphorus and fluorine. So here's the Lewis structure that we drew in the previous lesson. And now the second step always with covalent molecules is to determine the bond polarity. So we have to calculate the difference in electronegativity. We look up these values. Fluorine is 3.98. We're going to subtract off phosphorus, which is 2.19. And I always just subtract, I put the larger number first and subtract off the smaller value so that you don't get a negative number. And then the difference is 1.79. And this falls actually just slightly above the range of a polar bond, but this is still a polar bond. So anything above 1.7 they claim is ionic, but this is not ionic. Okay, ionic, you have to have a metal and a non-metal, and these are still two non-metals. So sometimes we just go a little bit outside of the range, and that's okay. Use the type of element to tell you whether you have an ionic or a covalent molecule. We know that we've got to come over to our structure, and we have to now indicate, because it's a polar bond, that the electrons are moving towards the more electronegative atom, which is fluorine. So we draw our little bond dipoles indicating that fluorine is slightly more negative than phosphorus. So phosphorus is more positive because those electrons are being pulled away. Now, step 3 is for us to look at the overall polarity. And if we consider what's happening here, we notice we have a movement across the molecule. So from left to right, that is equal. So those cancel out. But we notice that we have a movement going down and nothing's happening here. Okay, so at the top of the molecule, there is no pull because that set of atoms or set of electrons is not bonded to anything. So overall, we have an overall dipole that runs to the bottom of this structure, and we're always drawing that dipole in the direction of negative charge. Okay, so in this case, there is an overall dipole. We just drew it in, and this is what we would call a polar molecule.